Okay. So for this question, you have, let's say, so question 1 is basically just about concept of bootstrapping. All right. So it's just a conceptual question. So I'm just going to briefly go through this. Okay, so you have let's see. Okay, so you have some statistical distribution. Doesn't matter. You have some distribution, right? And you collected some IID random variables from this distribution, right? Okay. So then you have some, let's say, parameter of interest. So this distribution has some parameter, okay? And this parameter, you can construct functions of this parameter. For example, the simple one will be the parameter itself. You could think of something like square root of it or whatever, okay? Theta over 1 plus theta, anything, right? Anything that's a function of theta. So suppose you can estimate, so this is your, right, tested. So this is your statistic, right? Which is based on the data. So this is your data, right? So we use this to estimate, for example, it says to estimate this some function of theta, okay? And show how you can actually use bootstrapping to estimate the standard error of this statistic, okay? All right. So this is very simple, right? First is that you resample, right? You resample your x. So this is a vector, right? I just denote this by a vector. So resample this with replacement, right? Resample elements of this with replacement. So you generate what we call a pseudo sample, okay? Or it's also called a bootstrap sample. Then the next one is you compute T. So we'll resample this, okay? You can denote it with, you get this thing, right? This is actually a resampled, this is to denote this is actually some kind of resampled values for ith iteration, right? Then you compute T on this resampled value, okay? Right, and then after that you repeat 1 and 2 up to, let's say, 10,000 times, for example. Okay, for example. All right. So this will give you your bootstrap distribution, right? And once you have the bootstrap distribution, the SE of T of the statistic that you want is equal to the standard deviation of the bootstrap distribution, okay? Bootstrap distribution of T of X. All right, okay? So it's just, you just need to explain it conceptually like this, okay? This is basically just a description of the bootstrap algorithm, right? In a general way. Okay, and then after that, you are asked to use bootstrapping to correct for the bias, right? if your T of X is some kind of biased statistic, right, bias estimator for G of theta. So the simplest one may be like, for example, you use plug-in estimators. Plug-in estimators are usually biased, plug-in estimators, okay? So for example, theta, suppose Tx estimates theta, right? Then your plug-in estimator for theta square will be basically just this thing itself, okay? So this is what we call a plug-in estimator. It's very easy to do, but it is usually biased, okay? So you can correct the bias by either doing some mathematical statistics work, or if that is too complicated, we just use bootstrapping to correct the bias, right? So how do we correct the bias? So basically it is the same here, okay? We have this step, yeah, we also have this step, right? And also have this step. And basically the estimated bias is given by the mean, right? The mean of the bootstrap distribution. Subtract G of theta hat, okay? Right, okay? So this is the data, right? From this part, you have the data, you estimate it. So the bias is you take the mean of the bootstrap distribution, subtract this value, okay? And therefore your bias corrected estimator for G of theta is equal to G of theta hat everything minus the bias, right? So this becomes 2 times of G of theta, the estimate, subtract the mean of the bootstrap distribution, okay? Right, so that will allow you to correct for the bias. Okay, so this is the conceptual part, yeah? If you are asked to explain conceptually how to do the bias correction using bootstrapping, so this is how you do it, right? Okay, so I think this is pretty straightforward and also more or less available from the lecture notes already, right? So this is just some kind of reinforcement learning, right? Okay, so let's move on to the question 2. So for question 2, you have an exponential, right? Suppose let's follow from part 1, right? That the density is actually exponential, okay, with mean 1. Sorry, it doesn't say it's mean 1, right? It's just a rate parameter theta, right? Find the MLE of theta, and subsequently obtain the MLE of theta square, right? Show that this estimator is biased, but that the bias can be corrected by multiplying it with some constant, right? And then try to do some kind of assessment for how well bootstrapping correction for bias work. Then here you can make use of a mathematical statistics result that shows that the sum of NIID exponential random variables with parameter theta is actually a gamma, okay? So first we try to get the maximum likelihood estimate done first, right? So the likelihood function is basically your theta e of minus xi theta. You just multiply everything, right? Okay, let's multiply all the densities together. So you have power of n e of minus summation xi theta. Okay. So your log likelihood is n log theta minus theta summation xi. So you differentiate with respect to theta, you get n over theta minus summation xi set to 0. So of course you can check this, right? So if you differentiate twice, it is actually minus n of theta square less than 0. Okay. This just to make sure that this stationary point is actually maximum, right? Most of the time we just skip this step because usually are looking at for simple functions like this, it's almost the case that you will get a maximum, but it is better to check it anyway, right? So from here, this implies that your theta hat is equal to rearrange that, so you get n over sigma x this, or it is basically just the reciprocal of your sample mean. Okay, so this is your MLE of theta Okay, now how about the MLE of theta square? So MLE of theta square is basically very simple. It's basically the MLE of theta square. Okay, so there's a theorem that says that the MLE of G theta is equal to G of MLE of theta. Okay, so the MLE of this function is basically the function of the MLE of theta. Okay, so it's very simple, right? So so basically you're saying that the maximum likelihood estimator for theta square is equal to 1 over x bar square, right? Which is basically n square over summation xi square. Okay, so this is your MLE. Now, then we know that this guy here, right? This guy, let's say y, right, is actually gamma, okay? A gamma with alpha equals to n, all right? And then the scale parameter is 1 over the rate, okay? So how do we find the expectation? So we just need to do some basic mathematical statistics work to find the expectation of let's find the expectation of this. Okay. Therefore, this is finding the expectation of square over summation xi square, right? Okay. So this is my y, right? So basically, this is an n square integral 0 infinity, because this is y, right? So 1 over y squared, right? Because this one I represented with y, and y is actually gamma, right? So you multiply it that, so you get this is theta power of n over gamma n y n minus 1 e of minus theta y dy. Okay. Right, so then you can continue this. This will be n square integral. So this is 10. Okay, so let's focus on the y first. So you've got y n minus 2 minus 1, okay? E of minus theta y dy, okay? So we have to solve this integral, we just have to make it into another gamma density, but with a different parameters, right? So it has to have a matching parameter. So here we should have gamma n minus 2 And here we should have theta n minus 2, right? Because this part here is your alpha, right? Okay, the beta doesn't change, okay? Now, once you have this, we got to balance this thing out. So the theta is very simple. You just balance out with theta square. So this will cancel. And so how about this part here, right? So how do you go from gamma n to gamma n minus 2? So then when n is integer, gamma n is defined as n minus 1 factorial, okay? So gamma n minus 2 is basically a n minus 3 factorial, right? Okay. So basically this is, so how can you relate gamma n minus 2 to gamma n? So your gamma n minus 2 is equal to gamma n okay, let me see. So from here, so basically this is n minus 1, n minus 2 times n minus 3 factorial, right? So your gamma n is equal to n minus 1, n minus 2, gamma n minus 2, okay? So gamma n minus 2 is equal to, so you have your gamma n is here, right? So you write it as, so yeah, so you have n minus 1 here, n minus 2 here. All right? Okay, so from here, this integral actually, this integrates to 1. Okay, so you have n squared theta squared over n minus 1, n minus 2, right? So therefore, you rearrange this, you have expectation of n minus 1, n minus 2 over n squared theta hat square is equal to theta square, right? So then the bias correction is this factor. I think in the tutorial sheet, I think I have a typo. I think I put something like, I think instead of putting n minus 2, I just type n without the 2, right? So please correct that, okay? It should be like this, yeah? Okay. So there you go. So if you do mathematical statistics correction, this is how you correct it, right? By multiplying the plug-in estimator with this constant, okay? Okay, so then we want to see how the bias correction can be done using bootstrapping. So for this, you can go to Spectrum. I just uploaded an R script. You just go to Spectrum and download an R script, okay? Okay, let me just try to find the script. Okay, so this is the R script to perform the simulation. So of course I didn't specify what theta is, so you can try it for some different sets of values, like for example theta 1, but we'll just try it with theta 1, right? Of course, it can also be tried on theta 2 and some other possible values, okay? So here, this code here, maybe I just roughly run you through. Now, there are two steps here. The first thing is when we sample, we get a random sample of size 20 from the exponential, right? Because you have ID exponential random variables, okay? Right, that's the process, okay? So this part is fine, but this is only for one particular experiment, okay? That's why this is for this experiment. Then we use bootstrapping, right, to resample the data from this experiment, okay? Right, you can see that this is a bootstrapping code. Actually, I don't have to nest it inside here, but it's fine, all right? So in fact, I can create this bootstrap function outside of this function, okay? But I just put it here. And in this, so here, so this is just basically a function to do the bootstrap, right? Then after that, I create the bootstrap distribution, right? By repeatedly, okay? So I put X inside here, right? And then I resample and then I compute the statistic, right? Which is 1 over the mean of bootstrap sample squared, right? This is your plugin estimator in this case, okay? And then, so basically here I'm calculating the bootstrap distribution, and here this is the bias estimation, right? Take the mean of the bootstrap distribution, subtract the estimate, okay? So here is basically just of the data, so which is 1 over mean of X squared, okay? The bias corrected, so this is a bias estimation. So the bias corrected bootstrap estimator is take the plugin estimator, right? Subtract the estimated bias, okay? So this is a bias corrected form, right? And then I will return, since I want to compare the result between bias corrected and non-bias corrected, then I return both results, okay? The first one is bias corrected, the second one is the plugin estimator, right? Now this, so, and this thing I put it under a function called simul to indicate that if I run this once, I'm doing this experiment one time, okay? Which of course I have to do it many times, right? To look at the kind of variation. So that's why over here I have I simulate these things 1,000 times, right? To generate all the possible like large numbers of situations, okay? So after that, I can check the mean of the bias corrected value, all right, from multiple runs compared with those of the using plugin, okay? And then of course, I also check the variance, right? So with this, I should be able to compare their performance, okay, of using bias correction. So basically, this script here I can copy and then I run it in R. Okay, so it's here. So it will take a bit of time because I'm simulating this thing for 1,000 times, which is actually quite a bit because each run of this simul, right, you have 10,000 bootstrap iterations, okay? And I'm doing this 1,000 times. So altogether, how many operations are there? There are like 10 million operations being done, okay? 10 million iterations of codes. So this might take about a few minutes to complete. Of course, for initial assessment, I could actually just do this 100 times, right? But I tried it 1000 and it seems like it could complete in just a couple of minutes. So we just wait a bit for this. In the meantime, you can just look at the code, right? The code is not very difficult, all right? If you think of the code that's put here as a kind of process, right? Then you will understand it quite well. Okay, it's just basically trying to write up a set of instructions for a process and then ask the computer to do this many times. Okay. So we're going to be a bit patient and wait for a few minutes to get the output. Right, okay, so we have got the output here. Okay, so as you can see here, the bias corrected mean, right, for the bootstrap bias corrected estimate is 0.977. All right, and the one that's not corrected is 1.16. Okay, right, and the variance is actually smaller for the bootstrap corrected compared to the one that is not corrected. All right. If you just look at this, right? Okay, the first thing is what is the true value of theta square? It's 1, right? Because in this case, we set theta to be 1, right? So the correct parameter value here is 1. Now the bias corrected value is almost close to 1, right? So compared to the uncorrected, in fact, the uncorrected one is overestimating it by about 0.16, right? The bias corrected one is underestimating it by 0.023, right? It's about 8 times low, roughly about 8 times lower, right? The error, all right, compared to the uncorrected one, and also it has a smaller variance, okay, which means in this case, applying the bootstrap correction is actually a good decision here. All right, and then here what is the theoretical? So if this value, right, if you correct it by the factor that we derived just now, it should actually be close to 1. So let's try that. Just now the factor that we got was what was that? N minus, we got n. So let's see, set n equals to 20. So the factor just now was n minus 1 times n minus 2 divided by n square, right? Was that so, or it was it n squared? Let me check that. Okay, n minus 1 times n minus 2 over that. Then multiply by that value. So it should be close to 1. Let's go back to R. Okay, so this is the let's see, go back to R console. Sharing is possible. Bring your shared window to the top. Okay. Right, okay, so it is only, so this is the correction factor, right? That means instead of 1, so we correct it by taking only about 85.5% of this value, okay? So it should correct it to close to 1. So let's try that. Okay, so this is almost 1, right? Okay, so the theory is very powerful, okay? The theory allows you to do the correction in the most accurate way. But of course, it's not always that you are able to get the theory to work. It depends on the complexity of the parameter you're estimating, right? So bootstrapping will overcome all these problems, okay? So in fact, for some complicated functions, your theory, you are not able to do the mathematical statistics work. Then you will just rely on bootstrapping, right? So it will be better, okay, this way. All right, so all right, are there any queries about this question? So any queries about this question here? Okay, so I think since there are no queries, you should be okay, right? I hope. Okay. So then for the other two questions, 3 and 4, please check Spectrum later for the R code, right? That one is just basically some kind of revision on using bootstrapping, okay? But you adapt it to a different data set, right? So basically there's not much except you just need to recycle the bootstrapping code that you have with some minor adjustment for the data, okay? To suit the data, right? So that one, I don't go through it here, okay? So now I want to go through the question on the tutorial 7, which is the EM algorithm question, right? So that might take a bit of time. Okay, let's see this one. Okay. Right, so this is the EM algorithm question. I only have one question here, all right, because I know it will be, if you can do this one question, you pretty much, you kind of like have a good idea about the operational part of this algorithm, okay? Right, so in this problem, the first part is generally easier because the parameters have already been set, okay? The second part is to generalize it, so it will be more tedious, but generally it's just an extension of the first part, okay? And the first part, in this question, you have this following example. You have a large pile of coins, okay? Suppose you got a large pile of coins, right? And a fraction of them, alpha of them are fair coins, okay? Fair coins, so when you toss them, you get equal chance of head and tails. Then the remainder, they are completely biased coins, which when you toss it, right, they always give you the head. Okay, so for it has been those coins have been rigged already, right? So you no matter how you turn it, it will always give you a head. All right, so you then mix this pile, you mix up this pile, right? And then you randomly pick a coin from this pile and you flip to generate an observation, right? Okay, so let's look at the process, right? So then after that, you of course you can only count how many tails and heads are there. You are not able to know which coin belongs to which, whether it's a fair coin or a biased coin, because the label is hidden from you, okay? You can only see the outcome, right? But we can actually use EM algorithm to actually estimate the fraction of fair coins and biased coins, okay? That's the beauty of it. So in this case, we actually have a closed form solution for the EM algorithm, which I asked you to show that is equal to this value, okay? Right, so let's look at the process now. Okay, so you have two piles of coins, okay? So for example, you have a pile of coins here, okay? And then you have another pile of coins here, right? So here is alpha, here is 1 minus alpha, okay? Right, so this one will give you head with probability 1/2. This with probability 1/2. This one 1. This one 0. Okay. Right. So first thing is let's try to look at the observed likelihood, right? Okay. Now from here, right? If you start tossing the coin, right, you will get something like this. It could be this is what you observe. And you could get a hit. So this is what you get. This is the hidden. You may get a fair coin, right? Fair coin, then you get this. And then the next one you choose, you get a fair coin, you get a tail. Then if you see a tail, of course it comes from a fair coin, because the biased coin cannot give you a biased coin, no way to give you a tail, right? In this problem. So you get a head, it could be a biased coin, and so on, right? So this is what you see. But you do not see this, not seen. This is what we call latent, hidden. Right? We don't see, right? Okay, this one we see. This one we can't see. Okay, so the observed likelihood, right, would be the following. So what's the chance of getting a hit? If you don't know the labels, right, you don't know whether the coin is biased or not biased, the probability of getting a hit will be equal to the probability that you so this one you can actually use a hit from the biased coin or hit from the fair coin, right? So you add up both of them would be if, okay, so this one is condition on the bias coin, okay? This one you can condition on the fair coin, right? So if you have a bias coin, the chance that you get a hit is 1, right? So in fact, this one, you can actually, more accurately, you can write it as conditioning, right? Conditioning. Okay, with a conditioning, right? So here is 1 times 1 minus alpha, plus this one is 1 over 2 times alpha, right? So it will be 1 minus alpha plus alpha over 2, so it will be 1 minus alpha over 2, okay? And the probability of a tail, of course, would be alpha over 2, right? Okay, that's the complement, okay? So the observed likelihood will be 1 minus alpha over 2. Then you count how many of them, right? So because at the end, it doesn't matter, right? You're taking them to be independent. So you just need to count how many. So because each of these probabilities, right, they will correspond to either H or T, right? They'll multiply them together. So basically it's this thing raised to the power of the number of observed, this one is the head, right? So it's 1. This one is the tail. So this is 0, okay? All right, so this will be your observed likelihood. All right. Now, then how about our complete data likelihood? Complete likelihood. So complete likelihood would be if, so you have to imagine as if you can see the label. Which is the missing value, right? The missing value. So sorry, the missing data. Right? So here you would have the following so let me write it here. This is the likelihood, okay? Full. Right, you would have alpha over 2. This would be for the fair coin hit, right? And then you have alpha over 2 is the fair coin tail, right? And then you have the 1 minus alpha times 1, right? Which is the bias coin hit, right? And the other one, that's you can never observe it, right? So it's not present here, okay? So only these 3, all right? And then you just need to count how many of them are there, right? So this one is N1, 1. This one is N, let's say a head is 1, okay? This is N0, 1. So this will be N1, 2, okay? So your Nij, this one is the outcome. This one indexes the power, right? The coin power. Okay, so this part here is your full likelihood, okay? Which you can actually, so you have the full likelihood here. And then you can find the log likelihood, right? N11 log alpha plus N01 log alpha plus N12 log 1 minus alpha, okay? Plus a constant, right? The constant will collect these terms like the, that's why I don't put log alpha over 2, because the log of alpha over 2 is log alpha minus log 2. So the log 2 is actually a constant, which is irrelevant. Okay, so it doesn't play any part in the maximization step. So I can just move it to the constant. In fact, I can basically ignore this constant term. All right. So okay, so this is your log likelihood, right? And then we are now, so the most important part of EM algorithm is to be able to write this part. Important. You must be able to think as if you can see the label, and then write down the full likelihood equation. If you can't write this down, you cannot do the subsequent steps. So pay attention to writing down this, how you actually think about to write down the full likelihood model. This part here, you have to imagine that you can see the missing labels, right? What if you just think that, okay, don't worry that you can't actually observe them, because you're going to take expectation, conditional expectation to find out. Just think of it as if it is there, and then write it down, okay? And then now you can find the E step. All right, so the E step is the following. Okay, so we want to find the expectation of log of this given the incomplete data. So the incomplete data is NO, N1, and the parameter value. So this is the parameter vector, right? Okay, so I can just put I here. So this is just to denote a general iteration, right? So I want to find this step. And over here, you can identify which one is actually a just a minute, it somehow disappeared from my view. Okay, yeah, I found it again. Okay, so you have to find out which of these things is actually a random variable, this part here, right? Okay, so this part here is a random variable. This part here is also a random variable. And this part here is actually not a random variable, it's just a constant, because there's only one possibility, okay? You have NO and N1. These are the incomplete data, okay? But because when you got N1, it could be N11 or N12, right? But since over here in your full model, there's only N01, so your N0 must be N01, okay? So there's no ambiguity about this value, only these two, okay? So our expectation, our conditional expectation will focus on these two quantities, right? So we find the following, find the expectation of N11 given the incomplete data. Okay, so now, so here your N, so this part here, right? Now when you observe a head, right? It could be either, so this one is saying that it's coming from the pile of fair. So 1 is fair, 2 is biased, okay? So here, it could become, this one is coming from the fair part, right? So the probability of that is alpha over 2. Out of the total probability of getting a hit is alpha over 2 plus 1 minus alpha, okay? So this part is probability of getting a hit. This part is probability of getting a hit from power 1. All right. So therefore, this is your conditional probability, and then you multiply by the total. Okay. This will give you the expected value for N11, right? The expected number of fair hits from the fair coin pile. Okay. So it's just basically this conditional probability that you have to be. Actually, it's not that hard. Usually, this part here is the part from one pile, the other part from the other pile. Now, over here, since you also condition on the updates, right, the guessing value. So this part here is actually a value that's actually inserted. Okay, it's no longer, this is not a parameter value, but some guess value. All right. So this is your expected value. So the other expected value for N1, 2, condition on these two things, is basically, because this is the complement of the other, right? So here will be 1 minus alpha over this, okay? N1, all right? Okay, so, and basically you could write this as 1 minus the other, right? It's just the complement, okay? Whole thing. All right, so now you have already got your expected values, right? Therefore, you could write down the conditional expectation of the log of the full likelihood. So with that, let me clear some space here. Okay, so now let's see, I'll write it, I'll just use a notation. Let's say I call it Q, expectation of log L. So this will be, this thing here, the expectation is this one, right? So I will have the following. And 1 log alpha plus N0 log alpha. Okay, I might as well just write it N0, yeah? Then plus the other one is 1 minus this. And 1 log 1 minus alpha, okay? All right, okay, so this is my complete E step, yeah? You'll find that it contains the information, this this conditional information will go inside here, but then you will also retain the parameters, okay? This is the parameter in your model, right, in this case. And now we are ready to go to the M step. So the M step is basically we just maximize this expectation. So there's only one parameter there, so it's very easy to do. So basically you have, so over here is just, I'll just leave it out, right? The whole thing there, over alpha plus n0 alpha minus, so this whole thing here over 1 minus alpha, okay? Equals to 0, right? And then you can rearrange this. So let's try to rearrange it a little bit. Take this off. Okay, so let's do this. So we have 1 minus alpha times the following. N1 plus N0 is equal to alpha times 1 minus this, okay? All right, so then you rearrange this, you have alpha equals to, let's see, something like this. Right, over this whole thing right now. This whole thing here, you add here. There's actually an N1 here, right? So this thing you add here, it will cancel, right? Okay, so end up having N1 plus N naught. Okay, right, you can see here, right? This part here and this part here, when you rearrange, you will cancel off, right? So the N1 is here, then you only add this one, so you get N1 over N naught. So this basically is just your sample size N. Okay, so this is your updating equation, right? You then put I plus 1 here. Right, so your updating equation is based on this relationship, all right? Now, this is a very simple situation because you only have one parameter in this model, okay? So the updating will proceed very quickly, and then you will be able to reach convergence, right? Then you ask yourself, once convergence has been reached, what will the value of alpha be? So once convergence is reached, right? Convergence of alpha to, let's say, alpha star prime, right? Then that means alpha in this iteration and this, they all become the same thing, right? So therefore, you can replace that with the convergence value. So you just basically have this. Therefore, you now end up with this equation. 1 plus n naught over n. Okay, so then you can rearrange this to get the quadratic equation. So let's see what you will get here. You do this carefully, you will get over 2 over 1 minus alpha over 2 and 1 plus n naught. This is times n, okay? So this one is alpha 2 minus alpha and 1 plus n naught. This is n alpha dot, okay? Right, okay, so then you rearrange, you get n alpha at 2 minus this equals to alpha at. Right, so here you expand it, you will get n, okay, plus 2 1 plus. So rearranging, you get n this plus and 1 minus 2 n alpha prime plus n naught equals to 0. Okay. Right, so your alpha prime will be I think this one, plus minus square root of this minus 4 b square minus 4ac, right? So n naught. Something like that, okay? Let me check the question. Yeah, okay, so I think you have to rearrange. Okay, you will get something like this. Don't worry if it doesn't seem the same just now on the board, because there are some algebraic rearrangement that you can actually do. Or it is also possible that I miss out 1 or 2 terms, right? But you generally you get the idea, okay? You get a quadratic form, and then over here, since you have a plus minus, right? Okay, you will take the smaller one. Okay, because okay, let me see this one here. I think apparently the larger one will actually cause you to have some value that exceeds 1, right? So you take the smaller one, okay? In this case. Right, if you look at the algebra carefully, you take the larger one, you get some value outside of 1. Okay, so you take a smaller one, right? So that's why you can get a closed form solution in this question, right? and estimate alpha when this happens. So basically you just plug in, right? Okay, just plug in here. Right, then it asks you, does the value of alpha make sense, right? So you have to think about this a little bit, because over here you look at this. Like for example, question one, right? Situation one, you have 550 heads, 450 tails. So what do you think is a plausible value for alpha without calculating it? What do you think? You toss the coin 1,000 times and you got head 550 times, tails 450 times. Do you think alpha will be close to 1 or close to 0? Close to 0, right? Wait. This one is the head, this is the tail, right? So alpha is the power for the fair coin, right? So will alpha be close to 1 or 0? Think about it again. You see, when you have the tail, right? The tail can only come from the fair coin, isn't it? The bias coin cannot give you a tail. So if you see almost half of your coins, right, heads, almost half of your coins are tail. Is alpha close to 1 or close to 0? Yeah, it should be close to 1, right? Because well, it's only when it's close to 1, then you get to toss a fair coin, right? And then only you can see a tail happening. Okay, so intuitively, you'll know that for situation 1, your alpha should be close to 1, yeah? How about the second one? The second one, you get a lot of heads, right? But very few tails. So it's the reverse situation, right? A lot of these heads are actually coming from the bias coin, right? Because your tail, right, is only like 100 of them. So roughly this may be something around only 20% of fair coin, I think. Well, maybe let me see. You may only have about half of them, right? So let's say around 200, roughly 200 tosses from the fair coin. So you have roughly about 100 tails. So this is close to 20%, whereas this one is close to 100%, okay, for alpha. Okay, so here when it says, does the value of alpha make sense? This one you can verbally explain it, right? Based on the intuition that I mentioned just now, right? Okay, that's good. And now the second part here is you have to generalize the problem, okay? So to generalize this problem, let's go back to the writing board. All right. So now you have to generalize it. So you have to observe likelihood, right? So when you get a hit, right? It's either from the fair coin or it's from the bias coin, right? So from the fair coin, it will be alpha theta 1, right? Now you have theta 1 as the probability, okay? And this, so this one is theta 1, and this part here is alpha, okay? Then this one is 1 minus alpha theta 2, okay? Right? So probably you're getting a tail will be alpha 1 minus theta 1 plus 1 minus alpha 1 minus theta 2, right? And therefore, for your observed likelihood, it's probability of hit and multiplied by number of hits, and probability of tail multiplied by the number of tails, right? So this will be alpha theta 1 plus this, and 1 times alpha 1 minus theta 1 plus 1 minus alpha 1 minus theta 2 and 0. Okay. This so this log of the observed likelihood is then you have the log of the observed likelihood, which is n1 log plus n0 log. Okay, so this one is used during the updating. All right, the log of the observed likelihood is for the updating, right? Because later during the updating, this will be your update values, right? All these are your update values, and this is from the data. Okay, so you can calculate this log of the observed likelihood. All right, so this is later during the EM for the EM step, right? But to get the EM started, we want to look at the full, okay? The full data. So the full data will be, we need to know from the fair coin, we get a hit, right? So how many of them, right? So N1, 1. And then we have a fair coin, we get the tail. This is N10, right? And then also you do the same, right? For bias coin, and 2, 1. And this one, sorry, this is tail, B, and 2, 0, okay? So these are your latent variables, right? You can't actually observe this, but you can write it down, right? This is as if you know the coin has a label, an imaginary label that you can see. So over here, this will be, let me see. So actually, this is not conditional. This is a joint. This is actually a joint probability, right? Joint probability. So over here, that's why here you can write it in the conditional form. And so on and so forth, okay? This is actually a joint, joint, okay? And because of this here, you have alpha, theta 1, and 1, 1. This one is alpha 1 minus theta 1, and 1, 0. Over here is 1 minus alpha theta 2, and 2, 1. And 1 minus alpha 1 minus theta 2, and 2, 0. Okay? Right? So it becomes like this, right? So this is the critical equation that you have to write out in order for you to be able to proceed. So log of the full likelihood will be N11 log this. Okay, just write maybe. Okay, just write it like this: alpha plus log 1 log alpha plus log 1 minus theta 1 log 1 minus alpha plus log theta 2, and finally log this. Okay. Right, so this is your log of your full likelihood, so you get it like this, okay? Right, is it so far so good? This is basically the most important part of your EM algorithm, that you are able to write it down. Okay, and any queries about coming to this part, this stage?
No.
Okay, so now from here, they are ready to do the E step, all right? So let's go to the E step. Okay, now we can start the E step. So the E step, we have to identify which part to take expectation, right? So this part, we can take conditional expectation. Okay. These four things, right? So the first one is to take expectation of n1, 1, condition on the incomplete data, right? So, okay. So now this one, n1, 1, right? So what do you have? So here, this one is alpha theta 1 over alpha theta 1 plus 1 minus alpha theta 2. Okay, so these are all the getting the heads, right? This one is the head from the fair coin. This one is the head from the bias coin. This one is the head from the fair coin. So this part here will give you the conditional probability. And since you are also already conditioned on the updated values, so this has to be updated values, right? So these are some values that are being updated. Then I'll multiply this with n1, right? Because this is your conditional probability, and this is your total observed number of hits, right? Okay. So then you can have E of n, basically then 1, 0, condition on the incomplete data is basically just this one, 1 minus this whole thing, right? So here you can maybe say that this is T I theta I. So maybe just like that, Ti theta, right? So this will be 1 minus 1 subtract this Ti, okay? All right, to make the notation easy, right? And 1, right? Then the other one is expectation and 2, 1. Sorry, let me see. Is this sorry? This should be 2, 1. Okay, because you're talking about the success. Okay. Yeah, this one is talking about this one. Then I talk about 1, 0. Okay. So 1, 0 will be alpha 1 minus theta 1 over alpha 1 minus theta 1 plus 1 minus alpha 1 minus theta 2. Okay, and these are all your estimates, and multiply by n2, n0. Okay. All right. Okay. So you can call this part, let's say, z of theta. Let me see this one. Okay, so you call this z of theta, and therefore this part here you will get, you can call this as 1 minus z of theta and 0. Okay. All right. Okay, so these are the 4 expectations that you need to do. So you know in your E step for your EM algorithm is the conditional probability that is important. All right. So once you have done this, you are ready to write down the. So you have to write down a whole bunch of equations, right? So Q is the expectation of log L. Condition on the incomplete data. So this will be the N11. So the conditional expectation is this one. So you have T I theta and 1. Okay. And then you have log alpha plus log theta 1 plus this one is ZI theta log alpha plus log 1 minus theta 1. And then so on, right? So then you replace, right? Then you get a 1 minus Ti and all that, right? So you get this equation. And then you are done already because subsequently then you do the M step, right? M step, you take the derivative with respect to these parameters, okay? All right, so then you can solve for the stationary points, and then you get your updating equations, okay? Once you got the updating equations done already, you are ready to code them in the EM algorithm by recycling the code that I gave you, right? So you need to change the some of the things inside there, but basically once you have changed that, then the code will run properly, right? Okay, for that, I think you will, for the details, you can refer to the solution that I will post up later, right? Okay, so that's the general approach to doing EM algorithm. So the important part is to, the E part and the M part, they are not that difficult. Once you have got this thing done, then everything else should be just some careful algebra, okay? All right, okay. So are there any questions from you? You have to get your hands dirty on the EM question, yeah? Because just by looking at it will not help, okay? You have to get hands-on on doing it so that you have some idea what's going on. Okay? Right, okay, so I think you might need some time to digest this, right? Then I think the last thing I want to talk about is your assignment 3. So assignment 3 has already been marked and returned. Have you all received? Anyone else who has not received? Okay, so I think generally the assignment, most of you are able to complete it quite well. It's just that some of you actually skip the part on the theory when you're asked to do the importance. I mean the question 1, right? You just give me the R code and then that's all. I think, but I'm wondering like how you got the, because when I want to code up the result, right, you have to have some theoretical result to guide you. So maybe you got it, but you didn't include it. So I just want to let you know that for this kind of questions, right, you have to put in the theoretical result that actually let you to do the computation work. Okay, don't just give the computation result, right? And other than that, I think just the t-test. So when you do the t-test, don't just report the p-value, but you should report the estimates of the mean for the two groups. And then say which one is significantly higher. All right. And then you can attach the p-value. That will complete it. Rather than just saying p-value is such and such, and therefore reject, don't reject. That is something that people do 100 years ago, right? When people didn't quite understand t-test statistical methods. But we don't do that now, right? So we have to report the estimates, right? To get a clearer idea what is, yeah, sure, you say it's significantly different. So which one is larger, right? When you say it's larger, then you have to show the mean of the estimate of the mean, right? To convince people, right? Then the other thing is I noticed that because you do bootstrapping, right? Or permutation test, right? So when you do the permutation test, you might actually, or bootstrapping, I can't remember which one. So you get a p-value that is less. So you should get a p-value that is something close to the one that you got from the t-test. It won't change that much. Every one of you will get a different value because basically you are all taking different realizations of the possible combinations of the observation. So you won't get the same value, right? Slightly different. I noticed that in one case, there's a student who got a p-value that is 0.048 something, which is a little bit far away from 0.06, right? But it's still possible, okay? But in that case, right, we don't actually say that we reject the null hypothesis. When you get a p-value that is so close to the borderline, and you got it from a simulation, don't put all your faith in it, because you run it the next time, it will change, right? Okay, so because you have to realize that your p-value is actually just a roughly estimated p-value coming from the null distribution, from the simulated null distribution. How well your simulated null distribution represents the true null distribution depends on how many simulations you used. So generally you just use 10,000, right? So 10,000 is actually, it's okay. It almost finishes computing in the moment you press the key. But if you get some borderline value like this with 10,000 iterations, don't be like very happy about it, because you should be more rigorous by repeating this study, repeating the simulation. Like maybe you put like 100,000, right, 10 times more, and see what happens. Okay, so just caution on borderline p-values. Okay, you have to be cautious with that, and be very much aware that because you are doing bootstrapping or permutation tests and you are not able to sample the entire possible combination of data sets, you should be cautious when your simulated p-value is actually close to 0.05, right? Especially is those kind that are below it just by slightly a little less. Okay, so we don't want to make over claims, right? Okay, that's the only thing I think it might be useful to know. Okay. All right. Okay. So so then you can, I think, so you can check your continuous assessment score, which has been normalized and rounded. Okay, it's been normalized and rounded. So it's been posted there. If there is a mistake or you think there's a error in the computation, you let me know. Okay, I just check again. Right. Okay, so I think then in that case, just get ready for your assignment test next week, which is let me just check it again. Which is on next Wednesday, right? 10:30 a.m. So 1 day duration, right? Please check Spectrum again for the details, yeah? All right, please make sure you read the, let me just share this with you. So, okay, so I know sometimes you don't read these things. So, all right, so 3 things to keep in mind. These are the things that you have to have on your front page, okay? So this is the write down FE assignment, your matriculation number, your course code, academic session, semester date, and sign it, okay? Put a signature on it. Right? So then second part, you can handwrite. Because sometimes typing it in Excel, well, in Word, maybe you are pressured, you might not feel like typing it out. Just write it out, it's fine. Then you scan them, yeah, clearly, yeah, and submit as a single file, all right? In PDF file, yeah, please don't give me Word files, okay? Remember to give me the PDF file, all right? And then finally, number 3, you are to do the assignment on your own, yeah? So even though it's open book, but no communication between you, okay? Or you ask somebody to do it on behalf of you. So you have to complete the assignment on your own, and you can use all the open book resources that are available in the internet, and even all the script in the Spectrum, right? That means you have to study a bit for this, and not ask your friend, hey, how do you do this? How do you do that? If your friends ask you to do it, ask you things like that, you just decline, okay? Because you're supposed to do this on your own. You're not supposed to get pressure or friend to give you advice or anything, okay? And if your friend asks you to do that, you don't have to feel shy to decline, because I asked you to do it. Okay, there's no excuse to ask friends about advice at that stage. Okay, that means you have to study anything you want to discuss, do it before the day of the when you do the assignment, right? You can do your discussion group, whatever, to go through points which you feel you're still not getting it, so you can ask your friends, okay, to cross check on your understanding, right? But not during the time when you are doing it. Okay. All right, okay. So I think that's the important thing to take note. Right. Okay. So anything else from any of you? The next Monday we don't have lecture anymore, yeah. So you do your revision, okay? Next Monday is your revision, yeah. But you have questions during the lecture time, you can send queries in Flock, and then I'll try to answer it, okay? But otherwise, I don't have lecture because we already finished everything, right? So just you can do your revision, all right? And ask questions if you still have, okay? Okay, so that's all for today then. I think thanks for listening. So get ready, yeah? Okay. So stop the recording now.